Okay, so we're going to talk about less exciting subject here, which is semiconductors. Yes, my name is Donghoon Lee, and I'm from a Korean semiconductor company called SK Hynix. I'm in charge of our system IC business, and today I'd like to talk about some of the industry trends and try to relate them with what we do at SK Hynix. Okay, now let's start with this busy picture. Guess what this is? This is an internet map, and this shows all the connectivities between sites in the internet. Each node represents websites of the net, and actually this is an outcome of a project called OPTI, led by a researcher named Barrett Lyon. And by looking at this map, we can appreciate how connected we are with each other. And actually, the maximum distance between any sites in the internet turns out to be 90 clicks away. And that was some time ago. And of course, the number of clicks are shrinking as time goes. Now, from this picture, my takeaways are the first, we will demand more efficient communication means and technologies like 5G, and that will enable higher bandwidth and low latency in the net. And the second, as the communication becomes more transparent and more usable, we will start capturing and processing and sharing real-life data with each other. And this technology, called the Internet of Things, will become more prevalent as time goes by. So why am I talking about this? That's because the SK Hynix supports some of these functions with the devices. So in this talk, we will review what we have just talked about, the enabling technologies like 5G and the Internet of the Things, and then go into actual devices which SK Hynix is working on. Now, oops. So the video is not, so the video is being played. Okay, the first 5G, it will help create feature with a higher bandwidth and a low latency. And let's look at an example of downloading a movie in our real life situation. The 5G will shorten the download time by more than 400 times compared to an old technology, such as 3G technology. And when this technology becomes available, more useful applications will become more possible. We are showing two of such applications which are getting ready for deployment by our sister company, SK Telecom. On the left side, we are showing in the left video, you can see a remote sensing of medical application over 5G network. In the right video is a real-time robot control over 5G network. And those are actually services that we are thinking about deploying through our sister company, Telecom. The network is becoming more transparent to enable real-time or almost real-time enable feedback and control over the network. And that is going to enable many different applications. Okay, then the IoT and the drones. The IoT will improve our home automation, healthcare, smart vehicle, security, and so on. And the drones will revolutionize our logistics and distribution systems. Actually, during the CES, we even saw a drone for transporting humans. It will also improve our games, agriculture, emergency command, and so on. And these new technologies are not just a science fiction anymore. They are just around the corner. So where is SK Hynix in this revolution? In the hierarchy of technologies, from component up to application layers, we are in the bottom component layer. And in this component layer, we are currently working on sensors, memories, and power ICs. And in the rest of the talk, we will look further into those devices. The first, image sensors. In this section, we will cover 5 types of innovations that we are working on. We will look at smaller pixel, high sensitivity, high speed, some of emerging technologies, and computational imaging. Okay, this page shows a trend in image sensor technologies. The first one is the DTI, and it's which means a deep trench isolator. This technology improves picture quality by better isolating each pixels. The picture on the right top is our implementation of DTI. You can see each pixel is being isolated through insulator trenches that will reduce crosstalks among neighboring pixels. And the bottom picture, you can see an implementation of stack technology, where 2 silicon wafers are bonded and connected through TSP, meaning through silicon vias. This technology is being used to merge functions from 2 different wafers. And those are some of the technologies we are working on at this point. And then the pixels, they're getting smaller and resolutions are getting bigger. As you can see in the left graph, in time, pixel size curve is heading down and the resolution curve is growing up. For the pixel size, the current technology sits between 1.0 and 0.9 micron in size. We think the scaling limit will come around 0.8 micron, and that is something that we will be looking at in a few years. As for the resolution, the current technology is at about 24 megapixels in a sensor. But in the actual market, the adoption of 13 meg is most active. In line with the display technology moving toward the 8K resolution, the image sensors will grow above 33 megapixels in near future. Okay, now as the pixel size gets smaller, the resulting sensitivity gets more limited because the size of the photodiode becomes smaller and smaller. To counter such sensitivity degradation, we are working to utilize infrared to augment the regular RGB pixels. This solution will improve the picture quality, especially in the low light conditions, as in the example below. So by merging RGB image with the IR image, we should be able to come up with a sharper, with a higher definition, the image. The IR sensors will be buried under the regular RGB pixels for size reduction purposes, as in the diagram. And also in this kind of configuration, the IR output can be also used as a biometric, like a iris detection. Another way to achieve the highest sensitivity is through organic pixels. The photodiodes in the conventional pixels will be replaced by a thin panchromatic organic photoelectric conversion layer. Under the organic layer is a CMOS signal readout circuits, and this kind of structure will benefit us in two different ways. The first is a higher quantum efficiency. An organic material can bring the QE, the quantum efficiency, up to 100%, while the currently used silicon can only give us up to 70% maximum. And the second benefit comes from the minimum pixel, the crosstalk, due to the thin layer of the organic layer that we just talked about. In the silicon implementation of the photodiode, the depth and the thickness will be much, much bigger than the organic layer, which will result in a higher crosstalks. And those two benefits that we just talked about will give us brighter and sharper pictures. Okay, the speed. The high speed is another challenge in the CIS field. The CIS meaning CMOS image sensor field. A couple of years ago, Apple started capturing the images at the speed of 240 frames per second for the purpose of slow motion playbacks. Now we are trying to push the speed up to 300 frames per second, and this high speed together with the increase in the pixel depth from 10 bits per pixel to 12 and 14 bits per pixel is increasing the sensor's internal bandwidth requirements. And for that reason, we are getting ready to move into 40 nano copper process from currently available 65 nano process. And as the frame rate increases, the autofocusing becomes more challenging. There's less time to focus between the frames. So we need to come up with a scheme that will enable faster focusing. And the solution is to use 2 photodiodes per pixel and utilize the phase differential information from those 2 photodiodes per pixel. We call this new technology 2PDAF, and in the presentation there's a meaning for that. And this can also help us improve the higher dynamic range functions as well as the 3D vision and the light field applications. Now the holy grail of the image sensor application is global shutter function. When you capture a fast-moving images like a rotating fan blades, you will see a distorted image like in the top. The distortion is coming from a rolling shutter that will sample each pixels of a image in different times. So the current rolling shutter is optimized for a still or slow-moving object imaging for economic reasons. And what we are trying to do is a new technology, a new architecture called the global shutter, which will enable more accurate and natural image capture of fast-moving objects. The idea is to have the whole picture to be sampled and stored in some storage elements in the sensor, and have their values to be read out in sequence in time. So that way you will not have distorted picture like in the top, and instead you will be getting a very clear and very undistorted image as in the bottom picture. Okay, yet another trend in the imaging is called the computational imaging. And in this slide, you can actually see a very high-level roadmap of imaging applications in time. The apps will evolve from 2D to 3D, and we are in the process of doing that. And then AR, the augmented reality, and VR, virtual reality, and to computational imaging. The computational imaging will allow us to process pictures with a very high degree of flexibility. So how do we do this? In the conventional imaging pipeline, only the pure visual information is stored at the time of capture. But in the live field, the imaging pipeline, extra information such as depth information is captured and stored along with the visual information, and they are done usually per pixel basis. That extra information enables us with a flexible processing of images in later times. For example, the images can be refocused and sharpened and recomposed and so on. That type of processing requires heavy computation and complicated algorithms. And the Hynix is working on those as well. And if you look at the cameras are actually evolving toward the live field applications in time. Okay, now let's move to the second devices from SK Hynix. And in this chapter, we will take a look at the high speed and stacking and low power as the trend. So look at the DRAM technologies. Like logic devices, the memory technology has been scaling down. And these two graphs summarize how we have been leading the scaling efforts. In the left graph, you can see our SK Hynix process technologies moving down faster, and actually faster than the industry standards, ITRS technology roadmap. Currently, we are deploying 2Z node, which is like a 21 nano, and while developing 1X node, which is a 18 nano technology. And at the same time, the DRAM cell size is being reduced in time, as in the right graph. The current cell size is at 0.003 square micron, and it's going to keep going down. Okay, if you look at the power efficiency and the memory bandwidth, they've been dramatically enhanced. In the left graph, you can see how fast the bandwidth has been increasing in both mobile and the non-mobile devices. And in the right plot, we can see how the power efficiency has been getting better in time. In the NAND space, we've been seeing a whole lot of innovations also. We've been moving from 2D to 3D cell structure as a solution for density scaling. And currently we are working on 48 cell stacking, where actually 48 cells are being piled up on top of each other. So instead of shrinking down, we are also piling them up in 3D. And we will be shooting for 100 plus cell stacks by 2018 for better price performance from our devices. We have also been expanding our NAND solution offerings in the market. Here we can see one of our mobile solution roadmap. The roadmap goes from the eMMC 4.5 in 2013 to UFS 2.0 in 2015. And by 2017, we are planning to offer UFS 3.0 with a higher bandwidth and lower power requirement. Okay, the third device that we are focusing on nowadays is a power management device. Our power management device has been improving in both power efficiency and power density at the same time. And then the graph actually shows that from 2013 to 2015, the power efficiency increases and the power density increases at the same time. And we have also been working on energy harvesting technology to improve the power figures even further. Okay, now in conclusion, as in this the fresco in Vatican, the new world is about to be created. This new world is going to be based on our new technologies such as 5G, the IoT, and drones, enabled by higher bandwidth and lower latency from the web. SK Hynix has been working to provide devices to support those capabilities, and we will keep trying hard to improve the devices as we have reviewed in this presentation. That's the end of the presentation. Thank you.
Thank you. Does anyone have any questions or comments? We've got some time. As you covered such a wide range of topics there.
Yeah, it was.
Yes. Yeah.
Let's kick off.
Thank you very much, Don. You have clearly stated that the real timeline is from components to applications, which means end users. Now we are defining the Internet of Things set of products, services, which should provide. But I think we are now defining them with actual, which means old components. In the near future, we will have the new components that are now starting to become reality. And what do you think? Once we have these new components, we will have less services than expected, or maybe even the components will be so advanced and so low power consumption that even we can have even more services in the global Internet of Everything ecosystem, which is the trend. Components will really cause an explosion, real deployment of the Internet of Things, or maybe we will be still a step further.
I think our goal is to make the device to be very affordable, right? And then have device to be much more usable, right? So we are working to adapt our device to the industry APIs and industry standards and so on, so that the people from the non-electrical field, fields electrical engineering fields can actually start using those very easily. So I would say as time goes, the more service will be available through the IoT, the evolution, right? Does it answer your question?
Yes.
Thanks.
Hi, I have a question on the through silicon via, which is an amazing new element in semiconductors, and it allows you, as you described, to glue the best technologies on top of each other, so you can have an optimized DRAM, an optimized SRAM, an optimized digital core, for example, all different, all formed or fabricated in different technologies, but in terms of their interconnect, they're being connected by the via, so you get the best, performance / power kind of scenario by doing that. So my question is your company also working on through silicon via interconnect for the optical world? The reason I ask is in semiconductors, the largest power consumer is typically the I/O, and a lot of companies are going into optical I/O now, using the through silicon via to minimize that piece of the equation. Can you comment whether you're doing that or not?
Yeah, we are in the advanced technology. The level we are looking into the optical via through silicon via, but we see that we think it's going to take a little bit of time for actual deployment, and the prevailing technologies will be copper based or tungsten based, the vias for the time being, and maybe in about 5 years it will become that. And as far as the optical connectivity goes, the vias and then chip-to-chip communication, all those things are going to become, they're heading toward the optical. So I'm sure we will see the fruit of our efforts in our advanced the development efforts. Thanks.
So just following on a question that Bill asked here, I'm also very intrigued by going from 2D to 3D types of geometries. But as we go up into 5G cellular, we're now moving up into very high frequencies, much higher than 2 gigahertz. They're talking about 28, maybe 60. So we probably have to deal now with gallium arsenide or 3.5 materials and maybe silicon. Is there any work underway to look at 3D chips where you have a mix of silicon and 3.5 and gallium arsenide? Is that work going on? That makes sense?
Yeah, we've been manufacturing the multi-chip modules, right? Using different technologies. So I'm sure it won't be too difficult to merge them or stack them, through TSV or some technologies similar to TSV. We haven't tried that ourselves, but I'm sure there are people working on those, configurations.
New world.
Yeah.
Any other questions? We have time for one or two more. Otherwise, 11 o'clock. Yeah, we have time for a couple more questions. If anyone has them, next session will pick up at 11 o'clock. If not, we could take time for a break and thank our presenter.
Thank you.